Okay, so again, you're looking at the mechanism of the hydroboration process when our borane will be added to our alkene. No? So the first part will be the pi complex formation of your borane and your alkene, no, due to the the same orbital, the same geometry between the alkene and the borane rather compound. And what you will get here is a 4-atom transition state, and there is this bond formation between carbon and boron, and bond formation with carbon and hydrogen, and bond breaking process, boron, hydrogen, and bond breaking process of the alkene. So you have your 4-atom concerted transition state, which ends up to the syn addition of your hydrogen and boron to your alkene. And again, once you get your alkyl borane here, you can repeat on the process in such a way that this hydrogen sa imong borane will be substituted with your alkyl, no? Kanisiya without the alkene, of course, that's the double bond. So in this, once you get this one, you substitute this borane rather with alkyl borane. So one of the hydrogen is already substituted. So you repeat the process. And once the hydrogen already is replaced with this alkyl group, you repeat again the process here until all the hydrogen is already substituted with your alkyl. And then you will get your trialkyl borane. Okay, so let's take a look. Let's take a look at the orbital view of hydrogenation process. So here, this is what I mentioned earlier, no? That both of the alkene and the borane utilizes the sp2 hybrid orbitals. And if you remember, on the sp2 hybrid orbitals of your alkene, now the pi bond is formed by the sideways overlap. So you have here the p orbital of one carbon and the p orbital of another carbon, and the three orbitals is the sp2 hybrid orbitals. It's a hybrid between the s and the p. But one of the orbitals that is unhybridized is the p orbital. So there is an electron in both p orbitals and unhybridized p orbitals of the carbon atoms, and they form sideways overlap, and that is where the pi bond. Now, there is an electron, of course, in there. Both atom contains electrons, and sideways overlap of those two unhybridized orbital results to the pi bond formation. So the pi bond, you look at the pi bond, no, it lies up and below the plane of your alkene, of your molecule. And it's very unlike the sigma bond, no, where it's a head-on overlap. And so because this is sideways overlap, of course, remember the pi bond is much weaker than the sigma bond. Anyway, so you have this the unhybridized p orbital forming the pi bond. And you look at the boron, it also utilizes the sp2 hybrid orbitals. And boron contains vacant unhybridized p orbital. So which means there is no electron that resides in this unhybridized p orbital. So of course your p orbital, it looks like a lobe, no, which lies two lobes, no, you have in here. So once they are close to each other, they can actually form what you call as a complex, no? You have the same side of the p orbital will form a complex to the other, the p orbitals of your alkene, no? So they form a complex. You have your pi p orbitals of the alkene and your boron. So the donation of the alkene pi electron density to the vacant p orbital. So you have here, they have to be aligned, no, and they have to be oriented in such a way that they can easily donate the pi electrons from the pi bond of your alkene to the vacant p orbital of your boron. And because of that, now what happens is actually one of the carbons here will form a bond with boron using the pi electrons here. Okay, so they are on same side. So it's like the p orbital will form like a head-on overlap of the other p orbital of your boron, but in such a way that the pi electrons in the p orbital sa imong pi band will form like a head-on overlap here kani, no? So one of the carbons utilizes its p orbitals to form like a head-on overlap of the p orbital of this boron here, and that would result to a partial bond formation, and boron hydrogen would result to a partial bond breaking process, and the pi electrons would result to partial bond breaking process because it will be utilized to form a bond here, and a partial bond formation between hydrogen and carbon here, in such a way that you will get your boron added to one side and hydrogen added to the other side of your alkene. So as a result, no, you actually get the boron and the hydrogen added to the same side of your alkene, of your compound, of your carbon-carbon here, same side. We call that one to be syn addition of your hydrogen and boron. Okay, so you can read on this mechanism. This is what I have already mentioned earlier. So let's look at the stoichiochemistry of the hydroboration process. Transition state for the hydroboration requires that boron and the hydrogen atom add to the same phase. I've already mentioned that one. They actually add the same side, and we call that one to be syn addition. And why would that have the syn addition? Because in the transition state, no, we actually obtain 4 atoms involved in the transition state. Kani, no? 4-atom consortium transition state. It's a concerted reaction when the carbon adds to the boron using its pi electrons, and hydride will be added here. It's a concerted reaction, no? You get a 4-atom concerted transition state before you get your product, and that leads to the stoichiochemistry of the syn addition of your borane to your alkene. Okay, so here you'll see is you have an anti-Marconic addition with your borane rather. So when you say anti-Marconic you see here the carbon that contains a higher number of hydrogen, that this is where should have been the hydrogen be added, and the carbon containing fewer number of hydrogen, this is where the other atom should be added, but this is not the case. No, what happened is the carbon containing less number of hydrogen, containing higher number of hydrogens, or the carbon that is less substituted is the one that adds to your boron, owing to a less steric effect. No, when it approach, or when boron approach this side here, this carbon atom is much less sterically hindered as this carbon atom here, since there are 2 alkyl groups here that's being attached here. So this is a carbon that would be added to your boron. The one that contains a higher number of hydrogen is the one that will be added to boron, and the other side will have the hydrogen added here. And you notice here that this is already an anti-Marconic syn addition. Okay, so for the example, specify the alkene needed for the synthesis of which of the following alkyl boranes by hydroboration. So this one is very simple. No, you have to remember you have your 1, 2, 3, 4 carbon atoms, 1, 2, 3, 4 carbon atoms. You have your BH3 THF. No, so you have to remember unsa nga alkene. What is the alkene? Letter A. Anyone? The alkene is needed for synthesis of each of the following alkyl boranes. Anyone? Okay, it's like you have to be like a retro concept, no? So if you have, for example, you start with the alkene. Of course, to get your alkyl borane, the reagents that we need, of course, is BH3 in the presence of THF or ether THF, or if other ethers are utilized. So don't be shocked, no? THF is the usual one, but you can also use other ethers that I have already mentioned. I have mentioned other ethers. And then, of course, you have your alkene. And in this process, you have your boron added to the double bond, and the other carbon will have the hydrogen. So that pi electrons will attack the boron, which is electron deficient, and then the hydride from boron will be added to the positive carbon of your alkene. So letter A, what is your alkene here? Anyone? Donna. Can you suggest an alkene that is used?
Butane, ma'am.
Kinsa to? Okay, so you have the first part. So this is our product, okay? So what will be our reagents? This is simply the hydroboration process. So we simply have to, of course, our reagent is BH3. Tama? So you have your, let's see here, B. Okay, and of course you have your alkene, 1, 2, 3, 4. There are 1, 2, 3, 4, just have your alkene, no? And this is the one that the terminal one, or the one that contains a less substituted carbon, is where you will add your boron. And you notice that the alkyl groups here, it's not substituted. So most likely your alkene is not substituted. No, there's one of the carbon only is the one that's being substituted. So you have that, of course, in the presence of your your solvent THF. So what happens is that in the first process, you'll actually need 3 moles of this to get to have this one. Okay, so what happens is that ito na lang i-label si hydrogen. Yes, according si Mark, ba ito nag-ingon? Mark, ikaw ito nag-ingon? Your alkene is 1, 2, 3, 4. So that is butene, 1 butene. Okay, so when you have, once you have your, so this is the one that is less substituted. So okay, we will attack. We'll use this, attack our boron. And this is the one that attack this carbon here. Okay, so the carbon that is less substituted, there is the carbon that is less substituted is the one that is less sterically hindered, no, to attack our boron. So this is the one that will form a bonded boron. Get your alkyl borane. Okay, so you get your boron with hydrogen, hydrogen, and of course you have your 1, 2, 3, 1, 2, 3, 4. And the other one, ito na lang siyang tanawan. It should be on the same side, just have to, okay, hydrogen, carbon, 1, 2, 3, 4. Ay, sorry. Your carbon, your hydrogen will be added to carbon 2. So if this carbon 1, carbon 2, it should be on the same side. Okay. Okay, boron and hydrogen should be added in the same side. Your carbon 1, carbon 2, carbon 3, carbon 3. Always have to count para di mo mawala. Okay, and the next, of course, another mole of this. You have your another alkene. Parehara, no? Actually, I think you already get the point. Nadali ra siya. Plus, you have another alkene. Let's say 1, 2, 3, 1, 2, 3, 4. Okay, so your product is Copy. Okay, and then of course we use that one, the boron, arrow, the boron, this alkene, this end will add to the boron, and this one will add to the boron, and this one will add here. So for your product, you will have your kani substitutan lang natin siya og okay, so carbon 1, again you have to count carbon 1, 2, 3, 4. Okay, so the same side you will have your hydrogen added. Carbon 1, carbon 2, carbon 3, carbon 4. Okay, so it's carbon 1, carbon 2. This is where your hydrogen is being added. So another mole of your alkene. Is very simple, right? One, two, three, four. Okay, so put an arrow again. This one, that's right. This one will be added to boron, and the other one we added here. Okay, we use the electrons from boron hydrogen to add here, and your product is simply so ikatulad na ninyo mo tama. You'll get your kanina. Copy paste. Okay, so it's very simple process. It's a repeat process now. Okay, so the rest will be your problem sets. B and C, D, and then 8.12, 300 alkene. Okay, you can do this one. Oh my God, naglinog. Okay, naglinog siya. Wait lang. Okay, so that's problem 8.12. Let's go to the oxidation and hydrolysis of alkyl boranes. No? So the alkyl boranes produced in the hydroboration steps are usually not isolated. Kani, this one. Alkyl boranes from the hydroboration steps are not usually isolated. They are oxidized. So it's a one-path synthesis no, in the oxidation and hydrolysis, in the hydroboration and oxidation process of our alkane. No? So one step. So they are, after that, once you form your alkyl borane, you'll oxidize that and hydrolyze to form into an alcohol. You have your ROH and you have your alcohol, your OH added to your alkene, HOH, of course, you get your alcohol. So they are oxidized and hydrolyzed to alcohol in the same reaction vessel with the addition of hydrogen peroxide. So our second reagent, after we do the hydroboration, so this is our product now in the hydroboration process. It's an alkyl borane. So we have another step, which is the oxidation, and our reagent is hydrogen peroxide, H2O2. In the presence of aqueous sodium hydroxide, we have a base here. The medium is basic. So we have the oxidation and hydrolysis reaction that follows, and the process is that the boron is substituted with OH. So we'll look at the, of course, side product is the ONA. substituted boron here. So let's look at the mechanism, and just have to remember again on the reagents being used during the oxidation process. No? The oxidation hydrolysis test takes place with retention and configuration. So whatever the configuration of your alkyl borane will also be the same configuration of your alcohol at the end of the reaction. So let's look at the mechanism of the oxidation process for our alkyl borane. Okay, so first step again, you know already how to get your alkyl borane. So the second is that we will oxidize our alkyl borane in the presence of hydrogen peroxide ions. So hydrogen peroxide, where can we get that? Our source is the hydrogen peroxide, H2O2. Okay, H2O2. So there should be another hydrogen here. You have your OH bonded to each other. You have your hydrogen peroxide. But since we are performing this in the basic medium, one of the hydrogen in the hydrogen peroxide is abstracted. It's deprotonated hydrogen peroxide because of the base. Now the hydrogen again, kaning sa hydrogen din hinga wala diri, it's abstracted by the hydroxide ion. So our reactant na lang ng pabilin is the hydroperoxide ion, deprotonated hydrogen peroxide here. Okay, so again, your boron is electron deficient. It's a Lewis acid. It can easily accept electrons from any nucleophile. So our nucleophile here is our hydrogen peroxide ion here. It's very, very reactive. It's rich with electrons. So you can use this electrons from our hydrogen peroxide to attack here. And once you get our unstable intermediate, so you have your boron bonded to 3 bonds to 3 alkyl groups, and the 4th bond will be the boron OOH you have here. This is an unstable intermediate, no? So this is very unstable. Your system, this one, need to find a way to achieve a stable molecule. So how to do that? So boron will become negatively charged when it forms a 4 bond, no? So to stabilize our boron, it's very unstable for boron to have this, especially with the OOH here. What happens is we'll relieve this negative charge here, and to do that, the boron, okay, we'll use the alkyl, the R with the electrons from boron R to attack our oxygen, to form a bond with oxygen. Once the oxygen is formed here, okay, what happened is that the OH will leave, okay? So again, the boron accepts an electron pair from the hydrogen peroxide you have in there to form a stable intermediate, and an alkyl group migrates from boron to the adjacent atom as a hydroxide ion parts you have here. The alkyl groups can migrates from boron to the oxygen adjacent, and you have the configuration of the migrating carbon remains unchanged. So you notice that since you have here the OOH added to this boron, the configuration is still be the same. So we want to relieve this negative charge developed on our boron by migrating our alkyl groups to the oxygen. Once this migrates to oxygen, it will utilize our electron from R here. So because it utilizes our electrons here, you have your arrow here, you can aning electrons. So we will know which electron we'll be using to form a bond. So this is the one that we use to form the OR rather bond. So once it forms the OR bond, it's a concerted one. Once it forms a bond with the oxygen, the OH will have to leave and bringing with it the electrons given sa OO bond. So OH with 2 unpaired electrons and a hydrogen. So we'll have another electron pair here. It will recover hydroxide ion, and you have your alkoxy, boron alkoxy here, alkoxy boron here. And then repeat the sequence here. You use this instead of this one. And what will happen is that you get the BOR, BOR, BOR. Okay, so instead of OH, you will use the BRROR. Okay, and this is the one that will instead of RBRR, we'll use this one. Sorry. And you have your OH attacking your this. Okay, it will attack B. So this one is already substituted with OR at the end of the reaction, and it will attack again. So the R will be replaced with OR here. There is an alkyl sheet once the OOH is added. Okay, so next you have your OR, substituting R with OR here. Repeat the process, BOOR here, and then kanina po siya will attack with one R here, and you get the end product to be like a borate ester here. Okay. So how would the hydrolysis happens here? So once you have your borate ester, no, asa na to makita si OH, si alcohol. How do I cover our alcohol here? So since masaturate na si boron with the OR, okay, what happens is that the hydroxide will attack now the boron, no. You have to remember that again here, boron bonded to 3 groups of atom still becomes Lewis acid. There's still an vacant p orbital. It can attack the OH, will attack the boron. So what happens is that it will form the BOR, 3 atoms with the OH. No, so again, this one is unstable. So what will happen is that we will relieve the charge developed ng boron by eliminating our OR para mahimo siyang BOH. So you will check here, why would the OH live? Why would the OR live and not the OH? Of course, it's the OH that will attack, but the OR is actually a more good living group than the OH here. So here, the one that lives is the OR, not the OH. So once you have the OR and you have the OR will abstract the OH, and what will happen is that, okay, we'll use this electrons gikan kang OR and you abstract our proton gikan kang OH, and the electrons gikan kang OH will go to the oxygen. So unsa may driving force niya, I have to remember that in this case, hydrogen here is very electropositive. No, it's connected to an oxygen, which is an electronegative, and boron here being like an electron deficient. So the electron density gikan kang boron, and we'll try to disperse the charge ng boron. So this one, the hydrogen here is very electropositive. So the OR, the oxygen, can easily abstract the proton here. Okay, to form, it will use the electrons given to OR to form a bond. So you get your alcohol here in the process, and you will get your O minus and BUR. And to get more of the OR, okay, we just have to repeat on the process. So this is how the reaction ends. Okay, what you will see from the oxidation process is that what you will obtain in the oxidation process is an alcohol. Okay, kani general reaction niya, you get 3 moles of your alcohol from alkyl borane mo. Okay, so again here you just get 1 mole of alcohol, and you just have to repeat your process kani, and you get your 3 moles of alcohol. So the hydroboration oxidation reaction is regioselective. The net result of the hydroboration oxidation is anti-Markovnikov. Addition of water to an alkene, so it doesn't follow the Markovnikov's rule. And as a consequence, the hydroboration oxidation gives us a method for the preparation of alcohols that cannot normally be obtained through the acid catalyzed hydration of alkenes or by oxymercuration. You have to remember that oxymercuration, demercuration process, and the acid catalyzed hydration of alkenes now follow the Markovnikov's rule. But in the hydroboration oxidation process, it is anti to the Markovnikov's rule. And also you have to remember that in the hydroboration oxidation reaction, it's very stereospecific. What do you mean by stereospecific? There is a net addition of hydrogen and OH in the same manner. They are added on the same side. So if chirality centers are formed, their configuration depends on the stereochemistry of the alkene. So whether they become R or S, it will depend on sa starting material nato sa atong alkene. Okay, so if you remember in the Markovnikov's addition, where you only have your catalyst is just an acid and you have your water, when when water is added to your alkene, of course, our end product is our alcohol, right? So, for example, you want a secondary alcohol in your reaction, in your product, no? So what happens, it follows the Markovnikov's rule. The carbon that contains higher number of hydrogen is where your hydrogen is added. The other carbon in the double bond is where your OH is added. You have here. Of course, you have to remember on the process where, or the mechanism in which we follow this Markovnikov addition, we follow the formation of the carbocation in one of the first steps. There's always the formation of the carbocation, and the formation of a more stable carbocation is what favors the Markovnikov addition, or is the basis of the Markovnikov addition. Now, where the carbon containing a higher number of hydrogen will have the hydrogen added to it, and the carbon containing a fewer number of hydrogen is where the OH is added to it. Okay, so this is the usual Markovnikov addition. In the hydrogenation process, now it follows the anti-Markovnikov addition. They have two-step reaction, but even if there are two steps reaction, this reaction can still be happening in the same vessel. For example, in the first step, you have the hydroboration process, or reagent is BH3 into HF. You can have your diburane. Okay, what you will get in the first step is an alkyl burane. Remember, so the boron will have added to here. You have your hydrogen added there, and what happens is that later we will oxidize on the OR instead of R. We'll get our BOR. Okay, and that's the oxidation process, and later on we can eliminate the OR from our boron to get your ROH. Okay, you have here, and you notice on the difference between, this is one hexene, tama ba? And the other one is also one hexene. You notice on the product that's being obtained, no? Here, when you follow the Markovnikov's rule, you get a 2-hexanol. It's a secondary alcohol. If you follow the hydroboration oxidation process, you get a 1-degree alcohol here. And this is anti-Markovnikov. So again, depending on the kind of product that you would like to obtain, no, you have to choose a particular pathway to obtain your product. So for those, for example, if you want a 1-degree alcohol, but it's not possible with the usual system where you have the acid catalyzed hydration process to alkene, no? And of course, you couldn't get our 1-degree alcohol here. So we have to follow the anti-Markovnikov's addition, which involves the alkylboration and oxidation process. But you have to remember there is an anti-Markovnikov addition also that I have mentioned before, where we added, when you add our water to produce our alcohol, and if we have a peroxide added to it, and this is the one, no, peroxide. This is the hydroboration process, the anti-Markovnikov rule. And so see here, you notice that you have the same reagent, HF and peroxide in hydroxide solution. So what is our product here? Of course, the carbon containing the higher number of hydrogen. This is the one. For a normal Markovnikov's rule, this is where your hydrogen should be added, and this should be your OH, but this is not the case in the anti-Markovnikov, because this one is anti-Markovnikov addition. This is where you add your hydrogen containing fewer number of hydrogens, and this is where you add your OH. Again, this is anti-Markovnikov addition. So here, what you get is a 2-degree alcohol. If it should have followed the Markovnikov's addition, what you will get should have been a tertiary alcohol. But this one, you get a secondary alcohol here. Okay, it's very simple. So another important reminder is that in the hydroboration process, no, it's a syn addition. For example, you can find in the stoichiochemistry of that, particularly in your cyclic compounds, you have all the cis, hydrogen and boron, and of course, when you proceed that with oxidation process using peroxide and hydroxide in a basic system, what you get is a syn addition of HOH. And so if you look at on the stoichiochemistry of this, no, this is chiral, this is chiral. You have to be mindful, no, kung unsa imuhang gusto nga product. Okay, this is the net antimicronic. So this is the illustration of the hydroboration oxidation process. And the stoichiometry is very specific in this case. So they are, the HOH is added syn. It's a syn hydration. Get your alcohol in a syn manner. So because the oxidation step in the hydroboration oxidation synthesis of alcohols take place with retention of configuration here. Some retention of configuration. If you have your alkyl borane here, if your alkyl borane, you have here with this configuration. No, if for example this is R or S. If this is R, then this is R. If this is S, this is S. No, but I'm not checking. Now this is what I have. What we are seeing of this one involves in the oxidation process involves the retention of configuration once you get your alkyl borane. Okay, so the synthesis of alcohols takes place, the retention of configuration from the hydroboration oxidation process. And the hydroxyl group replaces the boron atom where it stands in the alkyl boron. This is the one that I have already mentioned. No? The same configuration. Kung unsay configuration ani niyang carbon here would be the same configurations once you get your alcohol from your alkyl borane. Okay, the net results of the two steps, the hydroboration oxidation, balik-balik, no, is an addition, balik sa kuan. Okay, so now you get it. Let's see. Specify the appropriate alkene and reagents for synthesis of each of the following alcohols. Specify the appropriate alkenes and reagents. Okay, you have here. You have a 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons. You have a 1 degree alcohol here. And this is like just a hydration. You can choose your alkene. So this is your alkene. Can have. So letter A, can you have a suggestion? What is our alkene? Is it alkene and our reagents? So including the reagents, no? Can you have any suggestion? Let's go. Ronel. Letter A. Okay, so you have here, you have to remember on your alkene. Okay, so how do we answer this one? Let's just answer letter A. Okay, so this is our product. And we can have our agent. We can have our okay, so what is our alkene here? Let's start with the alkene before our agent. If you have our product to be 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This is pentanol, 1 pentanol. Can you suggest what is your alcohol? Alcohol. Can you suggest what is your alkene? Kasi akong ditawag kanina. Si Ronel, no? Ronel?
Yes, ma'am.
Yes. Can you suggest unsa itong alcohol nga gamit? Pwede magamit here. Alcohol. Unsa nga alkene rather atong start pa din atong starting material for us to get this product 1, 2, 3, 4, 5. 5 carbon atom. 5 carbon alkene. Can you suggest an alkene for which our starting material will be? Again, this is an addition reaction. No? Just an addition reaction of water to our alkene. But depending on Marconico, follows Marconico addition or anti, no? Depending na sa itong additional reagent. But what could be our starting material here?
Ako, ma'am?